7.5 is on independent events. A lot of kids get independent events mixed up with mutually exclusive, so I want to make sure I try to do a very good job of explaining this so that we don't get them mixed up. Independent events are when one event has no bearing on the second event. It's almost as if they come in succession versus the idea of two events happening at the same time. With mutually exclusive, we're talking about when do two events happen at the same time or not at the same time. With independent events, we're looking at things that happen successively, so one event after the next. And when events do not have a bearing on the next one, such as flipping a coin twice, the coin has no memory, so to speak, and so it does not matter when you flip the coin the first time. It doesn't remember what happened the first time, so it's not going to have a bearing on the probability for the second flip. Drawing a sock out of a drawer 2 times. Obviously, that means with replacement, because if you're not going to replace the sock, then it definitely changes the probability. Then we're talking about something that's called dependent events, because the probability is changing from one to the next. Now, in terms of definition, A and B are called independent events if, I know that's the geometric way of saying if and only if, the probability of A intersect B equals the probability of A times the probability of B. That is the technical definition, and you must stick to it. Now, what do we need in order to do this? We need to look at a sample space. I know that's not your favorite thing to do, and if you refuse to write out or create the sample space on these questions, you will not be getting the correct answers. So make sure you're willing to write out the sample space. Secondly, calculate the probability of A, the probability of B, and the probability of A intersect B separately from each other. Do not just find these two right here and multiply them together, say that that's equal to the intersection, and somehow claim that they are independent events. That is going to be thrown out in any court of law, including mine. So, you need to find each one of these separately from the good old sample space. And if you can do that, why, then we can talk about the next step, which is actually to go to the definition and test them. Test them in the definition. In other words, does the probability of A times the probability of B really equal the probability of the intersection? If you can say yes to that, well, then they are independent events. If you have to say no, then they are not. They would be considered dependent events. So let's look at an example. Example 1. It says that event A, we got a spinner. On this spinner we have, oops, I'm going to draw it wrong. I think I already just did. Let's see if I can save it. Six equal spaces. So, quite honestly, this is no more different than rolling a 6-sided die. But we're spinning a spinner. If the first spin stops on an even number, that's what event A is all about. Event B is about the second event. The second spin stops on a multiple of 3. So look at the sample space. Now, obviously, you look at the sample space that I wrote out. I did not fill in everything. 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6. I did not go through the whole thing and do that. But I did calculate that the probability of event A, where the first spin stops on an even number, well, there's 6 of them in that row. There's 6 in the second row. And obviously 6 in the last row. which gives me a total of 18 out of the 36 possible choices, or 1/2. Probability of B. That's the second spin, is a multiple of 3. Well, that would be 3 or 6, so you're looking at 6 here in this column and 6 in this column, or 12 out of the 36, which is 1/3. You'll notice that I've highlighted the ones that are in common to both sets. There are 6 of them. So the probability of A intersect B is equal to 6 out of 36, or 1/6. So you'll notice that I figured the probabilities all separately from the sample space. Next thing I want to do is check. I want to check and see if the definition is true. Is 1/2 times 1/3 equal to 1/6? Well, the answer is yes. Therefore, the definition is true, and we can say that the events A and B are independent. So, definitely, from separate looking at the individual parts, we can show that the product is equal to the intersection. Well, that's not necessarily going to be true. In the second example here, we're talking about dependent events. That's when the probability of the second event is different based on the outcome of the first event. So if the probability changes from one event to the next, then they are dependent events. So let's take a look at example 2. In example 2, event A is the first spin is less than 3. Event B is the sum of the spins is less than 5. So I made out a sample space. This one I actually did have to I did have to look at the entire sample space, so I had to work out all the numbers. Now, the probability of A, the first spin, is less than 3. First spin is less than 3. Well, that happens to be all of these options in here, because the first spin would be a 1 or a 2. So there are 12 out of 36, or 1 out of 6 options there. Okay? Then we can look at the probability of event B. The sum is less than 5. The sum is less than 5. Well, that would be these values right here. And there are 6 of them. 6 out of 36. How did I get 1/6 on the last one? 1/6. Somebody hurt me. 1/3. I know all of you are screaming at home because you were saying, I was right. What's he doing? I'll have to admit, you were right. I apologize. Okay. So the probability of the intersection, the overlap, looks like they overlap in 5 of the 36 options. So the big question we want to ask ourselves is 1/3 times 1/6 equal to 5 over 36? That's the big question. Clearly the answer is no. 1 over 18 does not equal 5 over 36. So these events, A and B, are not independent. But dependent. Okay, the next part I don't need you to write down. We'll get to the part of the problem where you actually need to write it down, but I thought I'd give you a little bit of background to see some independent events in action. And in May 1983, an airline jet carrying 172 people between Miami and Nassau, the Bahamas, lost its engine oil, power, and 12,000 feet of altitude over the Atlantic Ocean before a safe recovery was made. I think it's important to note that everybody survived this event. When the warning lights indicating low oil pressure on all 3 engines lit up at nearly the same time, the crew's initial reaction was that something was wrong with the warning system, not the oil pressure. As one person stated in the Miami Herald of May 5th, 1983, they considered the possibility of a malfunction in the indication system because it's such an unusual thing to see all three with low pressure indications. The odds are so great that you won't get three indications like this. The odds are way out of sight, so the first thing you'd suspect is the problem with the indication system. Aviation records show that for the most common engine on a Boeing 727 airliner, there is an average of 0.04 in-flight shutdowns per 1,000 hours of running time. So the probability of an engine's failure in a particular hour is about 0.00004. Not very likely. Suppose the failures of the three engines were independent. What is the probability of the three engines failing in the same hour? Folks, this is the probability of three engines failing at the same time. So it's the probability of engine A failing, engine B failing, and engine C failing. And the probability for each one of these is this very small probability. Now, when you multiply that together, you get 6.4 times 10 to the negative 14th. That is so unlikely to happen that the most logical thing to say is, okay, something happened wrong with the electrical system. Well, in reality, okay, so this probability could be interpreted that if failures were independent, then about once in every, thousands, millions, billions, 16 trillion hours of flight would all three engines fail simultaneously. After the incident, it was discovered that a mechanic doing routine maintenance on the plane had failed to install 6 tiny rubber seals on the engine's oil plugs. The gaps this error created allowed all the oil to leak out when the engines were fired up. So they immediately lost all their engine oil right at the beginning, but they had enough engine oil to survive until they got up to an altitude and then lost 12,000 feet of altitude all at one time when the failures all happened. Not very fun, but everybody survived, except probably the mechanic's job. Can events be independent and mutually exclusive at the same time? That's a question that a lot of you ask. You get those two things confused, but keep in mind, mutually exclusive is about two events that could possibly occur at the same time, whereas we're talking about independent events where we're talking successive things, one after the other, so to speak. Let the probability of A be greater than 0 and the probability of B be greater than 0. Now, what am I saying? What I'm saying is they have to be possible events. If the probabilities were equal to 0, then the events would be impossible. But these events are definitely possible. So we got two possible events. Now, if they're independent, according to the definition, the probability of A times the probability of B equals the probability of the intersection. So you have a positive number times a positive number, which equals a positive number, which is definitely bigger than 0 because it's a positive number. I guess I said that a lot, didn't I? If they're mutually exclusive events, then we know that their intersection happening at the same time is impossible. That is 0. These two things contradict each other. So there is absolutely no way that the two things can happen at the same time. So they can't happen together. And please don't act like they can. And we'll look at 7:6 tomorrow evening.